My name is Kanella Panagiotopoulou, and today I will talk about my work regarding modeling departures from normality in meta-analysis. Before I begin, I would like to present you an outline of the following presentation. So in the beginning, I will briefly introduce you to the context of meta-analysis. Then I'll talk about heterogeneity and its implications. And then I will introduce you to alternative random effects meta-analysis models that relax the normality assumption. Then there is a simulation study that follows, comparing several of these alternative models, and then the application study in a real world case study. And finally, I will conclude by providing some concluding remarks and some directions about future research. So, meta analysis is a statistical synthesis of data from two or more studies comparing two interventions for the same clinical outcome. In meta-analysis, we have two main models: the common effect and the random effects model. In case of the common effect, we assume that all studies share a common underlying true treatment effect. While in case of the random effects, we assume that each study has its own underlying true treatment effect. Then we have the within study distribution, where the observed effect, yi, is assumed to follow a normal distribution with mean theta I, the underlying true treatment effect from each study, and sigma I square, which is the variance of the observed effects yi. At the second level, we have the random effects distribution, also known as the between study distribution, where in case of the common effect, as we said before, all studies assume to follow to share a common underlying true treatment effect. Therefore, theta i's are assumed to be equal to mu, the common summary effect. Whereas in case of the random effects, all studies share a common underlying true treatment effect, and they assume to follow a common normal distribution with mean mu and tau square, the random effects variance, also known as heterogeneity. So the assumption of the random effects is the main assumption that we mostly focus in this presentation. When we suspect small differences between studies in meta-analysis, then the common effect model can be used. For larger discrepancies, though, among them, the random effects model is considered more appropriate. However, when the differences between studies are very large, then no quantitative synthesis is recommended. And at these cases, a more qualitative approach is suggested, such as narrative description of the dataset at hand or subgroup analysis. Although the limits between these choices are not yet clearly defined, in this presentation we mainly focus on cases where we suspect to have very large differences between studies. I also remind you that the Cochrane Handbook had stated that meta-analysis of very diverse studies can be misleading, and that the presence of heterogeneity affects the extent to which generalizable conclusions can be formed. Additionally, a collection of meta-analyses combining both randomized controlled trials with observational studies had yielded up to heterogeneity values up to 1,000. So the first step is to identify heterogeneity. We can do that with several approaches, for example, through visual inspection with forest plots, with Cochrane's chi-square test, the I-square statistic, or even the true value of the tau square estimation and the prediction intervals. Then after identifying heterogeneity, we need to investigate its sources. We can do that either conducting subgroup analysis, which accounts only for categorical covariates, or with meta-regression, which accounts for both categorical and continuous covariates simultaneously. However, in both of these approaches, subgroup analysis and meta-regression, these covariates must be known and observed and specified prior to the analysis. So, one of the most common issues that we face in published meta-analyses is that most of them focus on the mean of the random effects distribution while also ignoring the random effects variance value. For instance, here I present you a hypothetical example of two simulated meta-analyses assuming a common mean and different variance. The one on the left-hand side is to represent relatively homogeneous studies, while the second one on the right-hand side is to represent highly heterogeneous studies. After conducting normal random effects meta-analysis, we observed the exact same point estimates in both cases, regardless the larger tau-square estimation in the second case. Additionally, if we have a look at the diamond of the second forest plot, we observe that the confidence interval only marginally crosses the line of no difference. Therefore, here in these two cases, most researchers focusing only on the mean of the random effects distribution would probably lead to similar conclusions, because this mean is just a point estimate which cannot be representative of the differences between studies. Another issue that we face when we have large tau square is that the prediction interval becomes very wide, losing its practical applicability about the effect of a future study. Now, let's go back to the random effects distribution. As we said before, under the conventional normal random effects model, we assume that the underlying true treatment effects follow a common normal distribution. However, in case of outlying studies, this distribution could be pretty skewed, or in case of effect modifiers that operate across our dataset, this distribution could have a completely unknown shape, just like this one. These effect modifiers can be known and observed or unknown and unobserved. In case that they are known and observed, we have two options. As we said before, we can either conduct subgroup analysis or meta-regression to try to further investigate the sources of heterogeneity. However, it is really common that even after accounting for all the available covariates in the dataset, for residual heterogeneity to remain. So, having all the previous as background, let me introduce you to our first one of published papers around this work, titled "Meta-analysis Models Relaxing the Random Effects Normality Assumption." It is a methodological systematic review and a simulation study, and it was published in the BMC Medical Research Methodology Journal last year. So, as we said before, under certain conditions, such as the presence of heterogeneity or outliers, and assuming a normal distribution for the random effects might not be the most appropriate choice. However, there are typical reasons for people using the random effects normality assumption even when this doesn't hold. This might be due to convenience, tradition, model simplicity, or software availability. Therefore, our goal was to conduct a methodological systematic review to identify all the available flexible meta-analysis models that relax the random effects normality assumption. Regarding the systematic review, we searched using a predefined search algorithm in PubMed, and then we looked at the citations of the included articles to identify additional eligible articles published elsewhere. Eligible articles were those proposing new methods, methodological reviews, simulation studies, and also articles providing some comments and on the properties and the characteristics of the methods of interest. From each article, we were interested in information regarding the setting and the type of the data that these methods were proposed for, regarding the underlying assumptions for its statistical model, and the theoretical properties and performance of the available approaches. The review was lastly updated on 14th October of 2024. So here I present you the flowchart of a systematic review, where in the beginning, as you can see, we have identified 1,278 articles through PubMed. But then, after screening the title and the abstract and reading the full text, we ended up with 21 eligible articles, where we added 6 more through hand searching. And finally, we ended up with 27 included articles proposing 24 alternative distributions for the random effects. So these distributions can basically split into 4 main categories. The first one is long-tailed and skewed distributions, where the models here, as you can see, introduce additional parameters, such as the location and scale parameters, which can be parameterized in terms of the mean and the variance of the random effects distribution. the degrees of freedom parameter, which determines the weight of tails, and the shape parameter determining the level of the skewness coefficient. For example, in case of the skew normal model, as you can see, the location and scale parameters are parameterized in terms of the mean and the variance of the random effects distribution, mu and tau square, and the shape parameter can also be expressed as function of the skewness coefficient. Now, in order to understand how the shape parameter influences the distribution, we observe that for positive shape parameter values, we have a positively skewed distribution, a distribution that is shifted more to the right, while for negative shape parameter values, we have a negatively skewed distribution, that is a distribution which is shifted more to the left. On top of that, we have also identified other skew distributions that allow to further express skewness, kurtosis, and tail weight. The second main category is a mixture of two or more distributions. Here we can combine same or different distributions in the mixture, and also the number of components, the component-specific parameters, and the weights should be defined either a priori or estimated through data-driven algorithms. The most common mixture model that we have identified is the mixture of normal distributions. This model can also be covariate dependent or not. And for illustrative purposes here, I present you the mixture of two normal distributions, assuming different component means and same component variances, using different but fixed weights. Another common mixture model was the common mean mixture distribution model, which combines two normal distributions this time with common component mean but different component variances. The first component variance is to accommodate relatively homogeneous studies, while the second one is for outlying studies. And here, for example, the weights were estimated proportionally to the number of studies within its component. We have also identified bivariate and multivariate extensions of mixture models, particularly useful for longitudinal data and diagnostic test accuracy meta-analysis. The third main category is a Dirichlet process mixture model, where the model here can suspect and create clusters of the underlying effects and determines the probability of all possible cluster assignments. This model can be fully characterized by two main parameters: alpha, the concentration parameter, whereas alpha increases, the random effects distribution is assumed to be closer to the Bayes distribution, and the Bayes distribution which determines the mean of the process. In other words, the Bayes distribution is our best guess of the distribution that the data points come from. This model is pretty flexible because as Bayes distribution, we can use any distribution we like, for example, the normal one. The Dirichlet process model can be seen either as a mixture of points by assuming a discrete distribution for the random effects, or as a mixture of distributions, most typically used normal distributions, by assuming a continuous distribution for the random effects. There have been suggested several approaches to model the Dirichlet process, but here I present you the Steichen breaking process, which further requires the specification of a truncation point that allows for a plausible approximation of the full process. On top of that, several extensions of the Dirichlet process have also been proposed, such as the conditional DP, which was restricted to have posterior median the mean of the Bayes distribution, and the polytree prior, which is a generalization of the Dirichlet process. It has a similar structure of the DP, but the weights were defined based on the tripartition of the space. And the last category is the beta distribution, which was proposed for diagnostic test accuracy meta-analysis, and the modified version the modified version of the beta distribution shorter take, was also proposed for meta-analysis that suspiciously lacks outliers. So overall, meta-analysis models assuming non-normal distributions for the random effects have been proposed in the literature, but they have rarely been used in published meta-analysis. This might be due to lack of software availability or lack of understanding of the more complex model assumptions. However, this project was a comprehensive methodological systematic review of all the available meta-analysis models that relax the random effects normality assumption. We provide also a detailed description about their properties and the characteristics in a consistent way. Now, based on the results from the systematic review, only few simulation studies existed comparing the proposed model with only one or two alternative random effects models under a limited range of scenarios, for example, without systematic exploration of the key model parameters such as the mean and the variance of the random effects distribution. And most of these models were gone under an early stage evaluation, which was restricted to theoretical developments, mathematical proofs, and simple examples. Therefore, we conducted a simulation study to evaluate the performance of several alternative meta-analysis models under a wide range of scenarios. Here we see the models that we used in the simulation study, where as you can see, they differ regarding to the framework they were fitted, the within and between study distribution, and to the priors they used for the key model parameters. Here we have the data generating process where we used three different shapes to generate the true study specific effects. So the distributions we used were normal, skew normal, and mixture of two normal distributions. We also assumed 22 scenarios in total, varying the number of studies, the true mean treatment effect to represent the absence and the presence of an effect, and the heterogeneity parameter using moderate and larger tau square values. Of course, all these values were based on empirical evidence. And then additional scenarios with only 5 studies were also conducted in order to assess the performance of the alternative random effects models under the cases where we have meta-analysis with very small number of studies. And for each scenario, 1,000 datasets were also generated. Now, I will present you the mean absolute bias of the random effects of the mean of the random effects distribution using all the models compared in the simulation study under a wide range of scenarios. For example, when the data generating distribution was normal, skew normal, or a mixture of two normal distributions, under 14 or 26 number of studies, when we assumed the absence or the presence of a treatment effect, and for moderate and larger random effects variance value. So, as you can see here, in case of moderate random effects variance, the mean absolute bias of the mean of the random effects distribution is relatively small, regardless the model that was used. However, as the random effects variance value increases, this bias becomes substantial, regardless the meta-analysis model that we used. Here I present you the percent relative bias of the random effect standard deviation, which was defined as the mean difference between the true tau and the estimated tau divided by the true standard deviation. So as you can see here, the percent relative bias remains mostly unaffected as the random effects variance value increases. But in cases where we have large tau square, as you can see, the Dirichlet process models that reach convergence seems to be the least biased. On the contrary, the frequentist T and the common mean mixture models seems to be the most biased under all scenarios considered. And here I present you the average bias of the estimated study-specific effects, using only the models that we were able to extract such estimates. Whereas you can see, once again, as the random effects variance value increases, this bias becomes substantial. Except for those two cases here, where we used a mixture of two distinct normal distributions to generate the study-specific effects, whereas you can see the Dirichlet process models that reach convergence seems to be the least biased. So, simulation studies showed that overall small differences between the compared models existed in terms of performance measures, but most importantly, the normal models did not perform worse than their more complex alternatives. Additionally, In presence of large heterogeneity, the mean of the random effects distribution was inaccurately estimated regardless the meta-analysis model that was used, supporting our theory that focusing only on the mean of the random effect distribution is misleading. When the data distribution is multimodal, mixture models may result in more accurate estimates of the study-specific effects, and simulation also revealed that in scenarios with few studies and moderate random effects variance value, all the Dirichlet process mixture of point masses models failed to converge, whereas the use of the normal distribution in these cases remained an appropriate choice. The simulation also comes with some limitations. For example, not all the identified models from the systematic review were compared in the simulation study. The true data generating distributions did not include all the different random effects distributions assumed by the compared models in the simulation. Using scenarios with more studies might have also improved the performance of some of the models. We only used a fixed skewness coefficient that might have not resulted in many highly skewed datasets to properly assess the performance of the skew normal models. And we only used a Dirichlet process with a mixture of point masses approach model and assuming a normal base distribution. Now we have the application of several alternative random effects meta-analysis models in a real-world case study. This article was submitted to the American Journal of Epidemiology and it is currently under review. Simulation studies showed that small differences in bias between models existed, with larger differences in coverage probabilities and precision. And most importantly, the normal models did not appear to be inferior than the other more sophisticated and complex models for most of the scenarios in our simulation study. To date, though, the real impact on the meta-analytic results and the potential benefit from using alternative random effects models remain unclear. So, by the application study, our goal was to explore in practice the similarities and discrepancies among several meta-analysis models that relax the random effects normality assumption using a real clinical example. To this end, we used a meta-analysis of 58 cohort studies investigating the IQ differences between children born extremely or very preterm and those born at full term. Standardized mean differences of the IQ children's scores measured between the ages of 4 to 7 years old were also used as effect measurement. And as you can see here, this dataset exhibits considerable variability across its studies. So the authors of the original paper, in order to try to further investigate the potential sources of heterogeneity, they conducted several meta-regressions, considering the median birth year as the most important covariate, and then adding additional covariates in the form of characteristics, such as the mean gestational age or the matching and adjusting status for socioeconomic characteristics, among others. They also performed subgroup analysis subgroup analysis based on the prematurity birth level, extremely and very preterm children, and then a meta-regression within each subgroup using the median birth year again as the most important covariate. However, none of these analyses managed to explain the observed residual heterogeneity between studies. So we applied in total 7 Bayesian alternative random effects meta-analysis models, including a normal and skewed extensions of normal and t-distributions, with prior specifications for the key model parameters presented on the right-hand side. And then we also used a mixture of 2 normal and 2 t-distributions with prior distributions regarding the key model parameters presented in the following table. And the Dirichlet process prior, using the mixture of point masses approach and assuming a normal base distribution with different priors for the key model parameters combined with 26 truncation point. As sensitivity analysis, we also applied models under both frequentist and Bayesian framework. So under the frequentist framework, we applied the normal model using restricted maximum likelihood estimator for tau square, the t-distribution model with maximum likelihood estimator, and a modified t-distribution, which was modeled as mixture of scale normal distributions. Then we used the common mean mixture model, which is a mixture of two normal distributions with common component mean and different component variances, one for the homogeneous studies and the second one for outlying studies, where the weights were estimated proportionally to the number of studies belonging to the component of the outlying studies. Then we also used an extended version of the common mean mixture model where the weights were expressed as a function of the additional variance coming only from the outlying studies, and another mixture of normal and exponential distributions where the weights were defined similarly to the previous model. Under the Bayesian framework, we also repeated our primary analysis using a skeptical prior for the parameters determining the mean of the random effects distribution. And we also used the truncation Dirichlet process model with a mixture of point masses approach, but deferring the Bayes distributions. We used skew normal and skew t, and different priors regarding the concentration parameter combined with several truncation points. So here I present you the main results of the application, where as you can see in terms of the mean of the random effects distribution, all models yield small differences, but regarding the estimation of the random effects variance value, the estimates are identical. Prediction intervals are quite large, regardless the meta-analysis model that we used here. And similar results to the primary analysis were also obtained using variations of these models, sensitivity analysis. The application study also showed that skewed and t-distribution models gave a negatively skewed, heavy-tailed, and highly peaked posterior distributions for the random effects, while models using the Dirichlet process priors yielded a multimodal distribution of the underlying effects and revealed the presence of clusters of studies with similar characteristics, as well as some outlying studies. So here I present you the heat map of the co-clustering probabilities using the Dirichlet process mixture of point masses model with a normal Bayes distribution. The co-clustering probabilities are the probabilities of two pairs of studies to be clustered together to belong in the same cluster. In the heat map, the columns represent the study names, while the rows represent the cluster assignment for each study and the study name. So as you can see here, the overall pattern suggests the presence of two main clusters, but with several substructures within the clusters. Additionally, the co-clustering probabilities exhibit low to moderate values here, suggesting uncertainty in classification. This is also supported by these studies here, where they have similar probabilities of being clustered in the first or the second main clusters. And we also observe that this study here exhibits almost zero probabilities of being assigned, of being clustered together with any of the other studies in the meta-analysis. So here I present you the forest plot of the estimated study-specific effects using the Dirichlet process mixture of point masses model with a normal Bayes distribution and the maximum co-clustering probabilities. So based on this representation, the Dirichlet process model identifies three main clusters of studies: the red, the blue, and the black, as well as some clusters, smaller clusters consisted of 2, 3, or 4 studies. At this point, we tried to investigate whether the available study level characteristics could potentially explain the resulting clustering. Therefore, focusing only on the main clusters, the clusters that consist most studies, we found that the birth level, the mean gestational age, the IQ test, and the matching or adjusting status for socioeconomic characteristics are the key characteristics that are associated with the resulting clustering. More precisely, we found that the red and the black clusters include high proportion of very preterms, but they differ in the mean gestational ages, as the mean gestational age for the black cluster is more than 28 weeks, while for the red cluster is below 28 weeks. Then the red cluster also includes mostly unmatched or unadjusted effect sizes for socioeconomic characteristics, and each study is also mostly used a short form of IQ test assessment. And the blue cluster has the highest extremely to very preterm ratio and the mean gestational age below 28 weeks, which may be partially explain its overlap with the red cluster. So here, although these characteristics may not fully explain the resultant clustering, it seems that they're related to these clusters, and of course, additional characteristics need to be considered. Nonetheless, here the Dirichlet process model was able to identify an underlying mechanism that differentiates the studies, something that was not obvious, that something that was obscured using the normal random effects distribution. So, differences in estimating the mean of the random effects distribution were small across the models in the application study, but the estimates of the between study variance were identical. The application also revealed that skewed and t-distribution models produced an asymmetric distribution of the study-specific effects, while models incorporating a test for outliers indicated approximately two outlying studies. Examining whether the proportion of extremely preterm children within the very preterm subgroup contributes to the observed clustering would be something really interesting. However, such data were rarely available. Restricting the analysis to studies published within the last 10 years resulted in slight reduction in the IQ difference between preterm and term-born children. And overall, results indicated that heterogeneity may be partially explained by the available characteristics, but of course, additional factors need to be considered. So overall, alternative random effects meta-analysis models have been proposed, but they have rarely been used in a published meta-analysis. Meta-analytic inferences solely based on the mean of the random effect distribution could be misleading because this mean can be inaccurately estimated regardless the meta-analysis model that was used. Our simulation study also indicated small differences between the compared models across various performance measures. But most importantly, the normal REML model, so the model that assumes normally distributed random effects with restricted maximum likelihood estimator for tau square, which is the most commonly used model in clinical applications, often performed similarly to more flexible alternatives under a wide range of scenarios. And alternative random effects meta-analysis models might not affect materially the summary estimates, but they may assist to investigate residual heterogeneity, that is, the heterogeneity that still remains after accounting for all the available study level characteristics as covariates. And these models can provide better insights into the distribution of the underlying effects and the interpretation of the meta-analytic findings. More precisely, models based on skewed distributions might be preferable in situations where the data distribution seems asymmetrical, for example, the presence of one or two outlying studies. For bimodal and multimodal datasets using parametric or semi-parametric mixture models can also offer a better understanding of the underlying data structure. And Dirichlet process priors can also help to reveal the impact of specific characteristics that may act as potential effect modifiers. And in this context, although the mean treatment effect is the primary parameter of interest in every meta-analysis, greater emphasis should also be placed on additional model-specific parameters which provide information beyond the estimation of the overall mean treatment effect. And finally, in small meta-analysis, more complex and flexible models may lead to overfitting without necessarily improving precision or coverage probabilities, whereas the use of the normal distribution for the random effects seems to be sufficient. To conclude, investigators could start with a normal model and consider alternative models as sensitivity analysis under the view of seemingly non-normal data. And overall, this work provides a comprehensive guidance on the use of the conventional normal random effects meta-analysis models, as well as several flexible random effects meta-analysis models, aiming to assist investigators to better interpret the meta-analytic findings based on the context-specific decisions. And some thoughts about future directions. I aim to develop a user-friendly R package, including all the advanced Bayesian alternative meta-analysis models, which would include an intuitive interface with sensible defaults and comprehensive documentation, formal statistical tests to assess the plausibility of the normality assumption, integrated model diagnostics such as MCMC convergence checks or posterior predictive assessments. It would also include flexible prior specification to support the expert informed and weakly informative priors for the key model parameters of each model, visualization tools, and for the random effects, posterior and predictive distributions, and model specific forest plots with tailored summary information, and of course, class representation with posterior membership probabilities in case of mixture models or semi parametric approaches. So here I have some references for you, and thank you very much for your attention. Of course, if you have any questions, I'm happy to answer.
Thank you very much, Kanella, for your very interesting presentation. I'd like to invite everyone who might have a question to write the questions on the chat. For the moment, I don't see any question. So probably I could start, initiate a discussion here. As far as I understood, your simulation study shows that although we have some more sophisticated approaches, the standard and possibly the easiest to apply method performs more or less the same. But I think the key message afterwards was like, okay, it is not only about the summary statistic, the summary estimate, but the more sophisticated methods can give some better insights in the results, like co-clustering probabilities and identify clusters. Could you please tell us, like, what is the point of the clusters? What are we supposed to do with the clusters after identifying them?
Okay, thank you very much for your question. So actually, the goal of semi-parametric approaches such as the Dirichlet process model is to identify clusters of studies with similar characteristics. That means that within each cluster, we try to find the subgroup which consisted of more homogeneous studies, and therefore the next step would be to probably conduct a meta-analysis within these studies, and that would result most likely to a reduced heterogeneity, and therefore this would have as a result the less wide prediction intervals, less wide, more precise estimates that would probably improve or lead the decision making as well.
Okay, so practically, this is like saying that instead of combining, let's say, a very big number of studies that might yield very imprecise results subject to high heterogeneity, then we can instead identify these clusters and conduct the analysis within each cluster, which will have around 10 to 12 studies,
Yes.
such as in your example, and potentially draw the conclusions based on the most homogeneous studies instead of combining a set of very heterogeneous studies. If I understand well,
Yes, exactly. Yes.
that can be a usefulness of these clusters. Okay, I still don't see any other questions, so maybe I could ask another question myself. What about these models, more sophisticated models, especially the Bayesian ones? did you have any convergence problems in your simulation or in your real life example, or all of these models converged and fitted properly without much
Mhm.
trouble?
So actually, I had some convergent issues and in the simulation study, and as you can see here, the NC indicated in the plot is non-convergence. And I mostly had issues with semi-parametric approaches, such as the Dirichlet process one, because and when we have a small number of studies and and small heterogeneity or large heterogeneity, these models are most likely they do not converge because they're so they're very complicated models that needs more studies because they actually make inferences based on the data at hand, and they include many parameters. So in order to properly estimate these parameters, you need more data. So that was the main issue. If you have a small number of studies and large heterogeneity, if you have small number of studies and small heterogeneity, then it means that you don't give enough information to the model so that it can identify clusters or to sign, I mean, for its features to sign. So that was the main issue in the simulation study. However, in the application, I didn't have this problem because I already had math studies, a 58 number of studies, and I also had considerable heterogeneity. It was 0.11. So the model had enough information.
Okay. So I have two more questions.
Mhm.
And of course, if I see any question in the chat, I will stop and give the room to the people who might want to ask. So in your real life example, you showed us the forest plot and you said that there is a considerable amount of heterogeneity across the studies.
Mhm.
Could you explain a little bit more why, how do you identify this considerable amount of heterogeneity? Why you say that there is considerable amount of heterogeneity when um, we look on this forest plot?
Yes. So when we look on this first plot, first of all, we see that this study here is further apart from the rest of the studies. So that means that this study is probably an outlier and its effect is much further from the rest. So this is one indication. And then we need to have a look at each study. So, for example, the effect of this study is completely different than the effect of this study or than the effect of this study, which means that this increases the heterogeneity. So if we have a forest plot and we see something like that, completely different effects, or the effects, some of the effects are point on the right direction, while some others on the left, that means that we most likely have large heterogeneity. And this was also verified after using the standard normal random effects models with a REML estimator where we had 0.12 heterogeneity value. So, yeah, that was another point.
Okay. But did you also try to do the prediction interval in this case to see the amount of heterogeneity, like in the summary result?
Yes, yes, we did, and we also did it here with with a Bayesian normal model, but we also did it for all of these models. So these are the prediction intervals for this data
Okay. So
set.
this, I so you have this prediction intervals. Okay.
Yeah, and they're very large, as you can see.
Yes, I see a lot of variation there. Okay, so my last question is combined, and the first part is whether, after all, uh, across all these models, you think that some of them, after all, they are not so useful. And the other question is that whether in either of the two publications that you showed us, you provide access to the R codes so that people interested to apply them can easily find your code and apply it to their own datasets.
So for the first question, I believe that Some models are more interesting, some models are more useful under certain conditions. So, for example, when you have one or two outlying studies, then it might be easier and might be more useful to use skewed extensions of normality distributions, because this would tell you where is the skewness, at which is it left or right skewed, the distribution. It also provides some information about the proportion of the outliers in the data set. There are also some frequentist models that identify outliers as well, and then they accommodate them in the estimating procedure with a reduced weight. So these models are preferable in case of some outliers, of few outliers. And then if you have prior knowledge that the data set consists of subgroups, then you can use either the mixture models or the semi-parametric ones in case that you don't know what is the factor that differentiates the studies. And regarding however, using semi-parametric approaches, you need to have enough data, and you need to, they can give you, yes, you need to have enough data, first of all, and then they can give you something meaningful. And of course, all these codes from both papers, from the simulation study and the application that we tried different models, are on GitHub, and they're open, publicly open. People can see them.
And the link is available at the respective manuscripts.
Yes, exactly. Yeah.